Hello, welcome to Chapter 6. This chapter is an introduction to probability. Now, when we do simulations, there's some process we have to go through. The first thing we do is we want to state the problem, state the assumptions, assign digits, simulate many repetitions, and then state our conclusions. For instance, if we want to make a simulation to find the probability that a basketball player who usually shoots 75% of free throws makes more than 8 out of 10 free throws in a particular game. So the first thing we have to do here is state the problem. And we could just repeat what we have here. But one, we want to find the probability that 8 out of 10 shots are made. Now, number two, we want to state the assumptions. Now, the assumptions here is each shot has a probability of 75%. So the basketball player doesn't get better as he throws or worse as he throws, being tired. We got to assume that each shot is exactly 75%. Then we have to assign digits. So to assign digits with 75%, we have to think of some way we can represent 75 with digits. What I would do is randomly pick numbers 1 through 4. I would say 1 through 3, he makes the shot. And number 4 means that he misses. Now we just have to move on. And well, first before we move on, let's actually do this. Hit math, go over to probability, go down to random integer, number 5, and we're going to go from 1 to 4, and we're going to shoot 10 shots. So if you didn't have mine, the setup wizard that I have here, you do random integer 1, comma 4, comma 10, and hit enter. And now what we have to do is figure out our data. So I would make a table more than 8 out of 10 that's greater than 8 out of 10. And over here it would be less than or equal to 8. So here they make 1, 2, 3, 4, 5, 6, 7 shots. So that would be less than 8. And then we just keep hitting enter. And it looks like I have another less than 8. Hit enter again. And it looks like there's 1, 2. It's exactly equals 8. So now we just keep doing this again and again and again. And that's our first one. That's not. So let's do 1, 2 there and then 1 there. So you want to simulate this many times. The more you simulate it, the better. But for the sake of the problem and time, I'm not going to have you watch me do 30 of those. So our observed probability with this small data set is 1 out of our 6 trials. She got more than 8 out of 10. So, so there's a 1/6 probability. So this is the simulated probability equals 1/6, which means 1/6 of the time that she shoots 10 free throws, she'll make more than 8 out of 10. All right. Now getting into the more theoretical probability, we have to define some things like the sample space as all the possible outcomes. An event is one particular outcome that relies on this random phenomenon. A probability model is a mathematical description of that data set. There's some rules in probability. all probabilities have to be between 0 and 1. The probability of the entire sample space has to always equal 1. The addition rule, if two A and B are disjoint, meaning there's nothing in common, you can just add those two probabilities together. The complement rule, the probability that it's not A is 1 minus the probability A. And the multiplication rule, if this only works for independent events. If they're independent events, uh, this is a rule that you can do. If they're dependent, the probability of A and B is the probability of A times the probability of B given A. And we'll talk about this in a little bit. Um, Now sampling with replacement and sampling without replacement. If you're sampling with replacement, you take something and then you put it back before you take another. Sampling without replacement, you just keep taking things out of the pot and you're not putting them back. This changes the probability because after I take my first one, this next one's probability is different because this first one comes out. Where when you sample with replacement, the probability stays consistent as you go through it. Now, union, intersection, complement, mutually exclusive, these are all terms thrown around. A union is everything in set A and set B. Left side is A, right side is B. We write it A, U, B, that's A union B. The intersection are the things that are in common in set A and set B, and we write it with this upside down U, meaning A intersection B. The complement is everything that's outside of A. Mutually or exclusive or disjoint, they mean the same thing. They're two things that have nothing in common. There's no overlapping parts. And yeah, A intersection B does not exist. There's nothing there. Now, one thing I want to talk about, just to go back to here for a second, whenever they're mutually exclusive, these cannot be independent. Because if I know my data sets have nothing in common, if I know that something is in set A, then I know for sure that it's not in set B. So knowing it's in A depends on my thoughts whether it's in B or not. So these cannot be independent if they're mutually exclusive. Or another way of saying it is these are always dependent events. Now the probability the Vikings and win a game is 55%. The probability the Timberwolves win a game is 25%. What is the probability that the Vikings win and the Timberwolves lose? Now, we can't really do the problem yet. There's something we're missing. We have to assume independence if we want to do this problem, because it doesn't say it anywhere. Now, if these are independent events, then we can multiply 0.55 times 0.25, and that's the probability that both of them occur. That's 0.1375. So this is Vikings, this is Timberwolves. What's the probability the Vikings win and the Timberwolves lose? So this is the probability that they both win. The Vikings win and the Timberwolves lose would be over here, which would be 55% minus that answer. So we do 0.55 minus that answer. So 0.4125 is the answer to this problem. On a certain AIDS test is given to 200 women in a village hospital. Its probability is a 0.004% chance of having a false positive. What is the probability at least one woman uh, of the women has a false positive? So first, let's find the probability that nobody has a false positive. The probability the first person doesn't have a false positive is 0.996. Probability the second one doesn't have false positive is the same, and you keep on doing that 200 times. So 0.996 to the 200 is the probability that no one has a false positive. 0.996 to the 200th power. So that's the probability that nobody has a false positive. 0.4486. So the probability that one or more will have this is 1 minus this, which is 0.5514. So that's not probability 1, that's the probability of at least 1. I should have put it on that side maybe. Because just 1 minus that would be the rest of the values. What's the difference between independent events and disjoint events? Remember, independent events, uh, knowing that something is in event A doesn't affect whether or not it's in event B. This, an independent always have to have some overlap. Disjoint never have an overlap. There's nothing in common in these two sets. Remember, disjoint are always dependent events. Deb and Matt are looking for a promotion at a law firm. Deb thinks she has a 7% chance of getting the promotion. Matt has a 5%, and she also estimates that the probability they both get the promotion is 0.3. So the probability they both get is 0.3. If that's Deb, that's Matt. If her whole circle adds up to 0.7, then that means 0.4 is over there. If his whole circle adds up to 0.5, then there's 0.2 over there. What's the probability that neither of them get the promotion? That's 0.7 and 0.9. There's a 10% chance that neither of them get that promotion. This A given B means the probability of A given the fact that B has occurred. And we can go back to this previous problem for a problem like this. What's the probability that Deb gets the job given the fact that Matt gets it? So when I say given the fact that Matt gets it, I'm just looking at this circle. So I narrow my sample space to be out of 0.5. So out of 0.5, the probability that Deb gets it, that's this section here, that's 0.3. So 0.3 over 0.5 is the same as 3/5, or 0.6. Now this is a conditional probability. All right, hopefully that's touched on the major issues of probability.